So back in chapter 2, section 3, we had a discussion of function. What's a function? But there's more. It just can't be an arbitrary transformation. There's something very specific that makes this a function as opposed to some other transformation. That's not a requirement. One-to-one functions are special. Onto functions are special. What makes them a function?
Yeah, it has something like each element of B goes to value.
Each value of B goes to a unique value of A.
Like you plug in value of A, it has to be value of B.
But there's one output for any input. No matter what that output is, they could all go to the same number. Constant function, right? Definitely not one-to-one, definitely not onto. Every output, every input has an output, and only one output. But that's a restriction. So let's get rid of it. I'm going to call the general idea a binary relation. A binary relation from A to B, so a binary relation of two sets, is any subset of the Cartesian product of those sets. And the sets could be anything. They don't even have to be the same size. They don't have to be anything in particular. They could just be anything. But what is the cross product A cross B, the Cartesian product? What's it look like?
For 1A, 2A, 3A, 4A.
All the possible ordered pairs, something in A in the front, something in B in the second, which means I can pick any subset you want. So, R. Let's see, I wrote down 1C, 2B, and 3C. That's a relationship between A and B. There are 16 possible ordered pairs I can make out of A times B, and that means technically there are 2 to the 16th possible relations here. Because each ordered pair could be in the relation or not. 2 to the 16th is not a small number. So, out of the 65,536 available to me, I picked this one. But if I write a relation, I'm really going to think of this as 1 is related to C, and 2 is related to B, and 3 is related to C. I can use this relation as a symbol. I could visualize this. One goes to C, 3 goes to C. 2 goes to B. There's my relation. I could make a table. Put an X in the row with row to column, right? 1 to C, 2 to B, 3, there you go. Now, the example we gave up here, is that a function? Why not?
Not unique.
That just means it's not 1 to 1. Think of where my uniqueness needs to be, Blaze. Everything in A should have an output. 4 doesn't have an output. 1 has an output, 2 has an output, 3 has an output, 4 doesn't have an output. So really, it's a partial function, a function whose domain is not actually A, but is instead a subset of A. That doesn't make much sense. If I have 1, 2, 3, 4, I should have an image for all of them. So this is not a function. The fact that it is not unique in this direction is not a problem. Functions means we can't have 2 arrows coming out of the same thing, because that would be a non-unique image. So let's consider this. What is my relation? I'm going to describe A is related to B if city A is in state B. So Pittsburgh is related to Pennsylvania, right? Is this a function? Beth, why not?
It's not defined for all the cities.
If there's a city in the United States, does that city have to be in some state? It's defined for all cities.
There's multiple cities with the same name.
Aha. There's a Pittsburgh, North Dakota. There's a Greensburg, Pennsylvania. There's a Greensburg, Kansas. Where's Miami? Ohio, Florida, Oklahoma, Arizona, Missouri, New Mexico, Texas, Indiana, West Virginia. They all have cities named Miami. That's not a function. A function is a special kind of relation. But a relation can take one item to many things. As we see here, I have 1 input, Pittsburgh, I got 2 outputs. I have 1 input, Miami, I got 10 outputs. Questions? X is related to Y if X equals Y squared. Is that a function? I got a head nod, I got a head shake. Oh, we got to figure this one out. Wait a minute. What's the input in this problem? X is the input. Y is the output. Pick an X. If X is 4, what's Y? Oops. What if X is -3? Oh, crap. So I'm going to have to be a little more specific. This is a relation. It's not a function. On the other hand, if I write this, well, then the only time that right-hand side is defined is when X is bigger than or equal to 0. So if I restrict my domain, and range, the input sets and output sets, to be positive numbers, that is a function. Questions? Way back in trig, I asked you to graph this equation, y squared equals x. Anybody remember what the graph of that looks like? The sideways parabola. And when you look at the square root graph, it's only the top half of that parabola. The restriction allows it to pass the vertical line test, which for algebraic functions works perfectly well. But for functions like our city and state example, or in this case, relations like our city and state example, the vertical line test doesn't really make sense. That image doesn't fit. So I don't have a graph the way I think of it in cities and states. Questions? That square root example, A and B are the same set. I'm going from the set of numbers from 0 to infinity to the set of numbers from 0 to infinity. A relation on a set is a relation from that set to itself. So in this case, with A and B being the same set, I can actually think of this as a relation on the set 0 to infinity. But I can do this for any set you want. I'm going to define the relation on the set of numbers from 1 to 4, integers, 1 to 4. A is related to B if and only if A divides B. A definition of a relation is an if and only if statement. All definitions are really if and only if statements. I would like you to write out the elements of this relation. How many ordered pairs are in this relation? I got 4, I got 6, 10, 8. All right, let's write them out. A is related to B if and only if A divides B. Pick an element. What does 1 divide? 1 divides 1, 2. Next element, 2. Does 2 divide 1? But 2 divides 2. Does 2 divide 3? But 2 divides 4. I'm done at that point. 3. And just 3, right? Doesn't divide 1, doesn't divide 2, doesn't divide 4. And then for 4, only divides 4 in this case. There's my divisibility relation. You could make a table. You could make some sort of chart. Clearly not a function. The input 1 has 4 different outputs here. Our sets don't have to be finite. Less than or equal to is a relation. If you give me 2 integers, you can tell me if the first one's less than the second one or equal to the second one or not. Similarly, we'll call this R1. Relation 2 could be strictly less than, right? Yes, ma'am.
Professional way of saying it.
Yes, IFF. If and only if. Sorry.
I don't mind it, I just want to make sure I knew what it
I thought I used that back in chapter 1, but it's been a long time, people. I'm sorry. I didn't say it was almost 4 months ago already. As I said earlier, when I have a finite set, then the Cartesian product has A times A elements in it, so that's cardinality of A squared, and that means there are an absolutely huge number of relations, even when A is a fairly small set. If A only has 4 things in it, then there are 16 possible elements of the Cartesian product, 2 to the 16th, 65,530. It's a big number really quick. Right? I think that's right. But I'm not just interested in relations in the abstract. I want to know some properties about relations. So let's think about some of the relations we've already seen. Let's add some terms. A relation is reflexive if A is always related to A. Always, for all A. So here's a question for you. The division relation. Is that reflexive? Yeah, A always divides A. So that's a reflexive relation. I just pulled them off the top of the page. Our relation R1 is that reflexive? I've got 3 people in the room who are talking to me this entire semester. Come on, the rest of you have voices too. Is this reflexive? Yes or no? Crickets. I love it. If it's not, that would mean that A is not always going to satisfy this if I put it on both sides. So is 2 less than or equal to 2? Is 17 less than or equal to 17? -5 less than or equal to -5. Okay, so this is reflexive. But relation 2 what about that one? That one fails to be reflective. So reflexivity, I don't know what the right word is here. The property of being reflexive means I'm checking, is A related to A? It doesn't have to be mathematical. I will leave it to you to define the relation child. We could do this biologically, we could do this adoptively, we could do this by families of the heart. I don't care. Is that reflexive? I'm not my own child, am I? I hope you are not your own child either. But again, doesn't make sense to me if we think either biologically or adoptively. Do you adopt yourself? Is that legally possible? I don't think so. Okay. A relation is symmetric if whenever A is related to B, then B is related to A. Again, let's think about the relations that have already gone by in our list above. Is divides symmetric? If 1 divides 5, does that mean 5 divides 1? Oh, no, that doesn't work, does it? How about less than or equal to? Again, no. If A is less than or equal to B, that doesn't make B less than or equal to A. And I would say the same exact thing for this, right? If A is less than B, then B is certainly not less than A, is it? How about our child of relation? Again, not unless you're a time traveler. For those of you interested in the joke, go look up the song, I'm My Own Grandpa. That'll help. On the other hand, some of these are less not symmetric than others. I know that sounds weird, but here's another idea based on symmetry. Now, you might just think that if it's anti-symmetric, it's not symmetric. But that's actually not what this says. This says something a lot more than that. If A is related to B and B is related to A, then A and B are the same. The only way to be symmetric is for the two objects to actually be the same thing. But wait a minute. Let's look at this relation right here. Suppose I know that A is less than or equal to B and B is less than or equal to A. What does that tell you? The only way for that to work in both directions is for A and B to be equal. That relation is anti-symmetric. On the other hand, the strictly less than is never going to work, right? If A is less than B and B is less than A, that's a contradiction. That's never going to happen. Look at our division relation. Suppose I know that A divides B and B divides A. Our division setup. I'm going to make an assumption. Let's just look at positive numbers for the moment. Throw negatives out the window for right now. Can I draw the conclusion that A and B are the same? If A divides B, what does that mean? Chapter 4, divisibility. Yeah. I don't want to use C. C is already going to be too close. Let's use a different letter. B is equal to A times K. For some integer K. Right? Well, wait a minute. If B divides A, what does that mean? Okay. Wait a minute. I've got B on this side. Oh, B is equal to AK, but A is equal to BJ. Regroup. B equals B times JK. What does that tell me about JK? We're dealing with integers. One of the only things you can multiply together as integers to get 1. 7 is prime. What am I multiplying it by to get 1? The only integers I can multiply to get 1 are 1 and 1. Or -1 and -1, right? But if my number is -1, then here that tells me that B is negative. Because B would be A times a negative thing. And A and B are positive. Well, wait a minute. That means that J is equal to 1. A equals B. Ta-da! Was it intuitively obvious? I don't think so. It took a proof, a direct calculation proof, but we proved it. If I allowed A or B the possibility of being negative, then this would be an option, wouldn't it? But then the only way this works is if A and B have opposite signs. -3 and 3. -3 divides 3, and 3 divides -3. So by restricting myself to just positive numbers, this relation was antisymmetric. Questions? A relation is transitive if A is related to B and B is related to C, then A is related to C. Again, I'm going to ask you, looking at our previous set of examples, which of them are transitive? Let's think about divides. Is that transitive? Why not?
Because, A, if A divides into B won't divide into A necessarily.
But I don't say anything about B dividing into A, do I?
Oh,
I say A divides into B and B into C. Okay, wait a minute. Suppose A divides B and B divides C. My goal is to show that A goes into C. So let's use the definition. A divides B means B can be equal to A times something. And B goes into C means C can be written as B times something. So can I write C in terms of A? Oh, wait a second. Let's just make the substitution here. And then regroup. K and J are both integers. What do you get when you multiply K times J? An integer. So if I call that thing L, then C is equal to A times L, and that means that A divides C. This is transitive, but I had to prove it. I can't just look and go, oh, of course it is. I have to check. How about our order, less than or equal to? Is that transitive? I'll just write out what it means. Suppose A is less than or equal to B and B is less than or equal to C. What do you know about A and C? In this case, I would hope that the conclusion here is one that is obvious. But my definition of obvious and yours are usually different. That's okay. If it works for less than or equal to, does it work for strictly less than? A is smaller than B and B is smaller than C? Yeah, then A is smaller than C. Yeah, that works. Child of. If A is a child of B and B is a child of C, is A a child of C? That looks like a very weird family tree, doesn't it? Grandchildren, yes, but child? No. Unless you want to say that however many generations still counts as children. I don't know how your family tree definitions work. So now we're going to have to go back and define a child of properly. Questions? If I have a bunch of different relations on the same set, like these are relations on the set of numbers. Divisibility is a set of relations, is a relation on the set of integers. I could restrict the less than or equal to the integers, then I would have three different relations all on integers, right? Or if I just looked at these, I could think of those as relations on real numbers, fractions, whatever set of numbers I wanted, right? Well, that means I can do all my set ideas. I can play all the set games that I played with sets. I can think about unions of sets, intersections of sets. I can think about the set difference. I can think about the complement of a set. And that allows me to define other relations. Relation 1 is the set of real ordered pairs where x is less than 1. Three different relations on the set of real numbers. So from the set of real numbers to itself. Let's see if we can describe some unions and intersections. R1 union R2. Help switch from set to logic. What word goes with that union idea? Or. So I'm asking for x is less than y, or y is less than x. What's the only thing that's not allowed? What about R1 union R3? It's either less than, or x is less than y, or x is bigger than or equal to y. That's everything, isn't it? R1 intersect. What word goes with intersect? Murmur, murmur, murmur. So y is less than x and x is less than y. That's the empty set. R2 intersect R3. Less than or equal to and less than. It's just R2. It's got to be in both to be intersection, right? Hey, wait a second. What is R1 complement? Say again? Thought I heard somebody mumble. R3. So I can play around with these sets. R3 take away R2. That's a set difference. What do I get? because it's less than or equal to and not less than. I can think of compositions. If I have R going from A to B and S going from B to C, then I can think of S composed with R from A to C. First do R, then do S. Wait a minute, that's a little circle, like F of G of X. A, S composed with R, C, if and only if A related to B and B related to C via S for some B and B. If we think of doing the same relation over and over, right? A divides B, B divides C, that's okay. I can do it the same relation multiple times. I can think of one relation to another. We talked about being a child of, right? A is a child of B, B is a child of C. Well, then child of child, grandchild. I can go as many generations as you want, right? By recomposing over and over. As a matter of fact, I'm going to make that sort of definition. R to the first is just R. R squared is R composed with R. So if I was doing child as my relation, then this is grandchildren. That's child of grandchild. That's great-grandchildren. As a matter of fact, I do it in general. R to the n plus 1 is R to the n composed with R. And the reason I mention that is because it turns out that powers of a relation are a way to check transitivity. It would be nicer if I could find a computational way to do this sort of power. But to do so requires me to create a computational representation of a relation. That is what we will do on Wednesday. I will see you then. A wonderful rest of your day.